Hey, IB Physics kids, Mr. Tima here. I'm going to talk to you about oscillations and waves. This is section 5.1, specifically about oscillations and waves. The hardest part about this section really is not the content itself. That's pretty um, juvenile in a way. The issue is you have to make sure that you're understanding the difference between terms like displacement, velocity, energy, kinetic, and potential, okay, and how it refers to the parts of a wave, okay? So I'm not going to go into detail on every slide. A lot of these slides in the full version of this is located on your Schoology. So you're welcome to do that and slow it down. Some of these slides I'm going to skip over, and we will be doing a pendulum demo in class, and we will be hitting this. So I'm going to hit the high points of this. So first of all, a simple pendulum. Something we need to understand is that a pendulum, if we allow this ball to swing back and forth, which you've all seen a pendulum or someone trying to hypnotize somebody with a watch or something, we have to assume that there are these spots A and B, and this O, or this knot as we like to call it, is equilibrium, or what we call the 0 point, or the O point. Okay, the standard. If we let this thing stop, it's going to stop, and it's just going to stay sitting there forever down there. So that's what we call the equilibrium spot. Again, we can see these in a lot of different variances about how things are done and how many pendulums there are. Again, this kind of just takes you through. So this is kind of how we move from the swinging of a pendulum to like how it would look on a sine curve. So basically, displacement, when that ball is sitting there at the 0 point, it has no displacement. As the ball is moved outwards, we get its farthest displacement. When we let go of that ball, the ball is going to start moving back and swing through the middle. So it's basically this. We're drawing it, and it's swinging back to the middle. Well, there it is back in the middle. Notice displacement is 0 again, but then it's going to go to the other side and stop for a second. That's its negative displacement, and so on and so forth. And you'll see that. Again, a pendulum, the idea of swinging back and forth is something called a period, the amount of time it takes to make one revolution back and forth. That is the same as something swinging around on a circle. Doesn't matter. It's the same idea. The idea of a pendulum swinging halfway out would be halfway around a circle, and swinging back to where it was is a full way around a circle. All right, equilibrium. Equilibrium is a position where the pendulum bob is would not be at, or would rest if not disturbed. Okay, but it usually has its highest velocity there. So there's some terms here. Amplitude, which can be seen as a big A. And remember, amplitude is the displacement from equilibrium to its highest point on the graph, not from top to bottom, but from the highest point from equilibrium or the lowest point, its largest displacement from equilibrium. Okay, it can be represented as a capital A, or what we like to call X naught. So we have this moving right here. So an amplitude, okay, would be at A and B. That would be its amplitude, and then finally the period, the big capital T. Remember, period is the amount of time it takes to make one revolution, or from, in this case, B to A, back to B. Okay, or you could say from A to B and back to A. It doesn't matter. So this is our standard equation for displacement. Displacement, x, is equal to the amplitude times cosine omega t. Now, omega, we'll talk about what that is here in a second. I don't really want you to focus on that so much right now. We'll focus on equations as we move to the end here. All right. Which ball has a larger amplitude? So we have to imagine these balls are moving back and forth. So which ones would have a larger amplitude, A or B? Take a guess. The answer is A. Right? Which ball would have a larger period? And the answer is also A. All right? A larger amplitude means it would have a larger displacement back and forth, or from equilibrium. And then in larger periods, a longer amount of time for the ball to go back and forth. Frequency. Frequency is how many waves are produced in 1 second, and it is measured in hertz. Okay, there's the equation. Frequency is actually 1 over the period. That means frequency and period are inverses of each other. If a ball has a time period of 12 seconds, what is its frequency? Well, if a period is 12 seconds, that means it takes 12 seconds to go back and forth one time. And we put 12 down here. So the frequency is 1/12 or 0.0833 hertz. So omega, I told you we'd get to omega. So omega is angular frequency. It's angular frequency. So how do we get that? Well, it's 2 pi over t. It's 2 pi over the period. So how do we get it's usually written as 2 pi f. Well, you got to remember, f is 1 over the period. So if we transform this, remember that period, you transform this or transcribe it, and you get omega is 2 pi f. So which ball has a larger angular frequency? Which which ball has a larger angular frequency? So you got to think which one's going to make more waves in less amount of time, and that's going to be ball B. So a pendulum completes 10 swings in 8 seconds. What's its angular frequency? Well, 10 swings in 8 seconds. So each swing takes, so its frequency is 0.8 seconds. It takes for one wave to do there. So, excuse me, the period is 0.8 seconds. We plug and chug, we get the frequency, and we put the frequency into the angular frequency formula, and we get that. Now, notice it's in rads per second because we're doing um, angular frequency, so we have to have it in radians. All right, find the, okay? So take a second, find the amplitude, the period, the frequency, and the angular frequency here. Now notice it's in centimeters, so just make sure that you understand that sometimes we refer to these in meters, but we're talking about centimeters here. So what is its amplitude, period, frequency, angular frequency? Come on back and we'll talk about it. All right, so looking at this, you should have seen that amplitude. Remember, amplitude is displacement off of equilibrium. So how far off of equilibrium it goes? You should have had the answer of 10 centimeters. All right, what is the period? So how long does it take to make one rotation or one wave? Well, this is one wavelength, and that took 0.2 seconds. What's the frequency? Now, frequency is how many waves happen in 1 second. Well, if every wave takes 0.2 seconds, we can get 5 waves in, or we can think of it as one frequency is 1 over the period. So that would be 1 divided by 0.2, and you would get 5. Or you can think about it, if it took 0.2 seconds to make one wave, we could get 5 waves in 1 second. Finally, angular frequency, we use 2 pi f. So 2 pi times 5, we get the answer of 10 pi rads, or you could multiply that and get like, the 31 point, so forth and so on. Do that math. All right. So again, with the pendulum, we got to think about energy as well. Okay. So remember, when this thing's swinging through, its maximum velocity is at the bottom. It actually has 0 velocity for a split second at the ends. As we pull it from displacement and let it go, it actually has 0 velocity here and maximum velocity at the bottom. You can also think about this with a spring. This would be equilibrium. This would be its displacement out here, or its amplitude out here. If we let it go, it would go through equilibrium down to the bottom to a max point, which should be equal but opposite of A, and so forth and so on. And again, the amount it stretches and compresses and everything results in the K value of the spring. Okay, this is where I'll have to walk you through in class. Don't really get hung up on the equations yet. Hold on to that thought. You can go back and look at that, but we're going to focus on the picture. This is a displacement versus time. So you got to think back to the beginning here where we took a displacement versus times and changed them into velocity versus times and acceleration versus time. We took the slopes of them, or the derivative of them. So look, if you have, this is displacement versus time. Literally, if you think of this as equilibrium, that's right down here, O. You see that? They mark it O. That's A and that's B. That corresponds to these letters here. So when they pulled this block up, that took it to 2 centimeters. Notice when it comes down, it goes down to -2 centimeters or 2 centimeters in the negative direction. Okay, and it would keep going like that forever and ever and ever if nothing stopped it. Well, here's the same thing, but this is the velocity. Notice it's the derivative or the um, shall we say, the slopes of those lines. Go back there and look. Look, if we took the slope of this part, remember we have to use tangent slopes. This has a value in displacement, but there's actually no velocity here. And the slope of the tops of these would be 0. This has a very large slope because when it travels through the center, it's moving at its fastest. When it gets to B, it stops for a split second. So notice it has 0 velocity down here. That's shown right here. 0 velocity, large negative velocity as it goes through, which again, look at the slope. This would be a negative slope. Okay, same thing, negative, back to 0 here. But now as it travels back up, it's going to have a very large value of velocity. And then when it gets up to where A would be, it would be at 0 again. All right. And then, of course, from velocity versus time, we can then calculate its acceleration, which is the inverse of, or the derivative of velocity or the slope. So let's just look real quick. This has a large negative slope. This has no slope or 0 slope, a large positive, and 0. Let's look right here. Large negative, 0, large positive, large negative, 0. Okay, it's just, or 0, excuse me, and so forth and so on. You can see that, okay? It's taking those slopes or derivatives of those points, and we'll walk through this. Again, here's just a great example of how you would calculate that. Okay, you can calculate using that to finding the displacement. And we'll talk about these as we move on. The same thing has to do with energy. Okay, if it's moving its fastest at the middle, if it's moving its fastest through equilibrium, then equilibrium is where we're going to have its largest kinetic energy. If it stops for a split second at A and B, then we'll have our lowest kinetic energy, but our highest potential energy. Okay, so again, this is just the kinetic energy. Here's the potential. We put them together, and you notice that they're perfect inverses of each other, which we've already talked about. They can be in phase. If the balls are moving together, swinging together, they're in phase. Their crest and troughs are lined up. If they're out of phase, they clank together. Well, a crest and a trough, and a trough are in opposite phases from each other. Again, that's the whole point of what juggling is. Okay, again, just showing you that the same thing of swinging a pendulum back and forth on a line is the same as swinging it on a circle, which we talked about. And that's why angular velocity is very similar to angular frequency. And there's a little animation for you there to show you how that would look. Okay, so again, these are your equations. I'm not going to get hung up on them. We'll talk about, I have a nice chart here at the end that will explain it all for you. Just kind of walks you through, though, how you do it. If you're somebody that really likes math and you want to see how this is broken out and it gives you how to break all this down, that's why I have it on here. Because some of us absolutely love to look at this and break this down. Some of you are looking at this right now and freaking out. Don't freak out. I have it all simplified, Mr. Tima version for you at the end. All right, so let's look at this, Doug, and consider velocity now. Where does the magnitude of velocity have the maximum value? At what letter would the maximum value of velocity be? That's right, that's at C. Where does velocity technically, for a split second, 0? There's actually two answers here, and it's A and E. Where does, now we're talking about acceleration. Where does the magnitude of acceleration have a maximum value? Remember, acceleration is a change in velocity. So we have to think, where's the greatest change in velocity? Well, that's A and E, because that was where the where velocity was changing from some speed to 0. Where does it have 0 velocity or 0 acceleration? Well, that's where velocity is at its highest or most constant value, and that's C. So again, these summary, these are your terms that you need to make sure that you understand. Okay. These are the six terms that you need to understand. So if you're looking at this and you don't understand what those six terms, you need to ask me a question. I walk you through again the math, but here you go. Here's the most important slide. This is probably the most important slide. These are your equations. This is your displacement equation. X, okay, X is equal, displacement is equal to the amplitude, X naught, equilibrium, from the displacement from equilibrium. So this could also be written with an A. Everything that's an X could be an A, okay? Cosine angular frequency delta t. And let's remember that angular frequency, so again, anything that has the x naught could be a capital A, or you could think of it as amplitude. Anytime we see the omega or the angular frequency, we need to think of that as 2 pi, 2 pi f. Okay? Or you could think of it as, if it's given to you as the period, but you should understand that frequency is 1 over the period, right? So that could be 2 pi over, goodness gracious, 2 pi over t. That's the same thing, okay? Velocity again is omega naught, or omega naught, x naught, which again could be amplitude, could be, could not be, and then you could be putting 2 pi f sign there. Acceleration, same thing, but we have an omega squared, same thing. This is in terms of time. So if they give you time in the equation, you can use these equations, okay? If they don't give you time and they only give you displacement, or changes in amplitude, like moving from this part of it to this part of it, then you can use these equations. So again, if you have time, you're going to use these equations to figure them out. If you're given displacement and don't have time, you're going to use these equations. I know that's a lot at you. We're going to have to walk things through. Here are your homework problems we're going to work through. Again, this is not an easy section. So make sure if you have questions, you ask. And again, until next time, Mr. Team is out.